Hi, today we're going to talk about the complex spectral theorem. Um, and just to remind you, way back in lecture 11, we talked about the real spectral theorem. And the real spectral theorem said that if you have a symmetric matrix, or symmetric real matrix, then it emits an orthonormal diagonalization. Okay, so this is saying kind of a lot of things. First of all, it's also saying that all of the eigenvalues are real. That's the first part of this, right? Lambda is a real matrix. So every symmetric matrix has only real eigenvalues. And then it's also saying that every eigenspace is the maximum possible dimension. So all the algebraic multiplicities equal all the geometric multiplicities. And it's further saying that the different eigenspaces with different eigenvalues are orthogonal to one another. So this is saying that real symmetric matrices are extremely, extremely nice. And it's very easy to state it. You just state that it admits an orthogonal diagonalization over R. Right? In other words, all these matrices are real matrices, which also says that the eigenvalues are all real, right? And so we're going to learn the complex version of this theorem, so where we allow complex entries in our matrices. Technically, we haven't defined that yet, though, so we'll let C m by n be the vector space of all m by n matrices with entries in the complex numbers. Okay. Um, and we'll oftentimes use this notation, just the usual notation, where this means that the z ijth entry sits in the first, or the ith row and the jth column, right? M by n, so there should be n columns. But now we're allowing all of these entries to be complex numbers, not just real numbers, right? Okay, and we want some notion of like a symmetric matrix. So for a real matrix, I mean, actually for any matrix, a symmetric matrix is one that's equal to its transpose. But it turns out that those matrices are not the correct nice analogs in the complex case. Instead, we're going to want to define the conjugate transpose. Okay, so this definition still works. So maybe I should just say A in C m by n is still called symmetric if A equals A transpose. So that's still the definition. If you swap the rows and the columns, you get the same matrix. But those are not as nice as the ones that are covered in the complex spectral theorem. So we'll define a new thing. So the conjugate transpose of the matrix A with complex entries is defined to be you take the transpose and then you conjugate every entry. So this is a matrix in C n by m. Right? In other words, it's the matrix like Z1 1 bar, but now you've taken the transpose, so this one is not Z2 1 bar, Z3 1 bar to ZM 1 bar. This one goes Z1 2 bar down to Z1 n bar, and we still end at NM bar now. Okay, so you just take the transpose and then you conjugate every entry. And it turns out that this will be the correct notion that we'll need to say the complex spectral theorem. I guess we should give an actual real life example, I guess. Let's do it with a non-square matrix. So if A is, I don't know, 1 plus I, 3, 2 minus I, 3I, pi, 4 plus I or something, then the conjugate transpose, which by the way, I haven't introduced the notation, we'll use the star notation, just like for the conjugate transpose of a vector. You take the transpose and then you conjugate every entry, which means that all of the imaginary values get negated. Negative I, 3, 2 plus I, negative 3I, pi, 4 minus I. Okay, and we know several properties about transposes, and we know several properties about conjugation, which means that we know several properties about the conjugate transpose. So, for example, if you take the conjugate transpose of a product, right, this means that you're taking the product, you're transposing it, and you're conjugating every entry. But we know that when you transpose the matrix AB, it's the same thing as B transpose A transpose. And conjugation doesn't matter what the order is that you do it in. So this will end up being B star A star. You should just check this for yourself on some small matrices. You'll see why. And that's also true for vectors, right? So if you take AV, that's a vector. You take its conjugate transpose. It's the same thing as the conjugate transpose of V, which we defined last time, times the conjugate transpose of A. Okay, so these two just follow from properties of transpose and conjugation. Okay, and so the important definition for us is going to be the following. So a matrix A in C n by n. So here, square. We're only making this definition for square matrices because it will only make sense for square matrices. Is called Hermitian. Hermitian, if it's equal to its conjugate transpose. Okay, so you should think of this as kind of like the matrix is symmetric, but it's not symmetric. It's equal to its transpose plus you've conjugated every entry. But notice that for the real case, if you have a real matrix, then the conjugate transpose is the same thing as the transpose, right? So remark, if A is actually a real matrix, then the conjugate transpose is just the transpose. So for so A is Hermitian if and only if it's symmetric. If it's a real matrix. Oops. Right. So this R is important here. It's only because it's a real matrix. So this does generalize the notion of symmetric matrices to the complex case. The point is that you can also, symmetric complex matrices also generalize the notion of symmetric real matrices, but they won't have as nice properties as Hermitian ones. I guess technically this one also should be n by n. It only makes sense if it's square. Otherwise, there's no chance it equals its transpose. Okay, so this generalizes the notion of symmetric matrices in R n by n to C n by n. And it turns out that these Hermitian matrices will actually be the ones that have the nice properties. So in some sense, this is the correct generalization. Okay, I guess we should look at an example of something that's actually Hermitian. So just like for symmetric matrices, the diagonal entries can be anything because the conjugate transpose condition doesn't put any condition on those. But when you have an off-diagonal entry, then across the diagonal, it needs to be its conjugate. So now if I conjugate and transpose this matrix, I will get back the matrix itself. So this is Hermitian. It's equal to its conjugate transpose. Okay, and basically the spectral theorem is going to hold not just for symmetric real matrices, but all Hermitian matrices. So it will kind of recover the spectral theorem for real matrices as a subcase of the complex spectral theorem for Hermitian matrices. So the first part, or one of the parts of the spectral theorem for real matrices was that all of the eigenvalues were real. You had no complex eigenvalues for real symmetric matrices. Turns out this is true for all Hermitian matrices. So, maybe I should make this a remark, I guess. We will recover, or maybe I'll say we will generalize the real spectral theorem for symmetric matrices, maybe I should say the spectral theorem for real symmetric matrices. To Hermitian matrices, which are a generalization. So the first part is the following results. If A is a Hermitian matrix, and Z is some vector in Cn, then Z star AZ is real. Okay, so we're going to use this in a second to show that every eigenvalue of a Hermitian matrix is real. Okay, so here's the proof. So basically we just take the conjugate of this thing, right? So suppose that A is Hermitian and Z is a vector in Cn. If we take the conjugate transpose of this whole thing, then, well, you reverse the order and you take the conjugate transpose of each of the elements, right? So this is going to be Z star star. But of course, if you take the conjugate transpose twice, you get back the original matrix or the original vector, because taking the transpose twice gets you back to the correct orientation. Taking the conjugate twice gets you back to the original complex number. So this is just Z star A Z. Maybe I'll keep the star here, but since A is Hermitian, it's equal to its conjugate transpose. So this is just Z star A Z. Okay, so in other words, this quantity is equal to its own conjugate transpose. But what is this quantity? This quantity is a complex number, right? The point is that this matrix is n by n. This vector is n by 1. This vector is 1 by n. This is a complex number. And it's a complex number where when I took its conjugate transpose, I got back the same thing, which means that it's real, right? So this thing is a complex number which is equal to its conjugate transpose. For a number, that just means it's conjugate. And this implies that this thing is real. It'll stay like this. Okay, so this is another way to think about what a Hermitian matrix is. It's one where if you set up this sort of analog of a quadratic form, as you change the vector z, it always spits out real numbers, even though the matrix itself is complex. So it's another way to think about what a Hermitian matrix actually is. Okay, but we can use this result to show that every eigenvalue of a Hermitian matrix is real. Okay, let's call it a proposition. Every eigenvalue of a Hermitian matrix is real. Okay, so here's the proof. So suppose that A is Hermitian. And let's consider an eigenvector eigenvalue pair. Right, so let's suppose that lambda, and remember, in principle it could be a complex number, is an eigenvalue with eigenvector, and let's call it z. Right, so I suppose I have an eigenvector eigenvalue pair for A. Right, this means that AZ equals lambda z. That's just what it means to be an eigenvector with eigenvalue lambda. But now just multiply by z star on the left for this particular z. Right? So then z star AZ equals z star lambda z, but lambda is just a scalar, so this is lambda z star z. But z star z is the square of the norm of z. In particular, it's always going to be a real number. So this thing is a real number. Or sorry. So this whole thing we know is a real number. But also we know that this length is going to be a real number. And that means that lambda has to be a real number. Right? So maybe I'll just say that by the previous proposition, this thing is real. And also the length of z squared is real. These two things together say that lambda has to be real. So for a Hermitian matrix, every eigenvalue is real. And this again recovers the result for real symmetric matrices, that every eigenvalue of a real symmetric matrix is real. Okay, so I guess there's a little example in the notes. We might as well do it. So let's consider the following Hermitian matrix. We can compute, just like for, this is just linear algebra, to compute its eigenvalues, we just take the characteristic polynomial. So if we take the determinant of a minus ti, that's the determinant of 2 minus t, 3 minus 3i, 3 plus 3i, 5 minus t. You'll get 2 minus t times 5 minus t minus 3 minus 3i times 3 plus 3i. So you'll get 10 minus 7t plus t squared, and then 3 minus 3i times 3 plus 3i is 9 plus 9, so plus 18. So it's t squared minus 7t plus 28. No, there's a minus, right? So 3 minus 3i times 3 plus 3i is plus 18, so there's a minus 18. So it's actually plus, or minus 8, which is equal to t minus 8 times t plus 1. So the roots of this are 8 and negative 1. So this Hermitian matrix does indeed have real eigenvalues, as it should. Okay, so one part of the spectral theorem was that all of the eigenvalues are real. The next part of the spectral theorem for real symmetric matrices was that the different eigenspaces were orthogonal to one another. That was true for real symmetric matrices. In fact, it's true for Hermitian matrices. So here's the result. So if A is Hermitian, if it equals its conjugate transpose, and AZ equals lambda Z, and A Y equals mu Y, where right, lambda is not equal to mu, and Z and Y are non-zero. Actually, it doesn't even matter. They could be 0. But of course, if they're 0, what I'm about to say is going to be true. Then the inner product of Y and Z is equal to 0. Okay, so if Z or Y happen to be 0, then this is automatically true. But if they're non-zero, then they're eigenvectors, right? So this says that eigenvectors from different eigenspaces are orthogonal. Okay, so what's the proof of this? So we're going to suppose that AZ equals lambda Z and AY equals mu Y. right? With a lambda not equal to mu. Now what I'll do is I'll take this equation and multiply on the left by y star. So then y star az equals y star lambda z, which is just lambda y star z, right? Now what I'll do is I will, so I'm trying to show that this thing is 0, right? So now I'll take this equation and I'll star it first, right? So also ay star equals mu y star. So in other words, y star a star equals mu y star. But a is Hermitian, so y star a star is just y star a. Now I'll just multiply on the right by z. Y star a z equals mu y star z. So what does this say? It says that this quantity is equal to this quantity and this quantity. So the pink and the blue thing must be equal. Equals mu y star z. And since lambda and mu are different, this means that y star z has to equal 0. Okay, so if you actually go back and look at the proof of the real symmetric, in the real symmetric case, you'll see that it's basically the same proof. It's just you don't need to worry. You don't take stars. You just take dot products. But it ends up being basically the same proof. Okay, so I guess we should look at this example again because we bothered to do it. So the eigenvalues are 8 and -1. Let me just copy this whole thing over to that slide. Why not? There we go. So let's take a look at the eigenspaces. So E8 is going to be the null space of A minus 8i, which is the null space of -6, 3 minus 3i, 3 plus 3i, -3. Okay, now this thing will have rank 1, because it definitely doesn't have rank 0, and it definitely has to have a null space. And so I can take the basis vector here to be, if I want, 3 minus 3i, 6. Because that's going to work. Which is also the same thing if I want to simplify this a little bit as a span of 1 minus I, 2. Right? Okay, and this one does look a little bit different than the one in your notes. But if you multiply this one by 1 plus I over 2, you'll get the one in the notes. So multiply to get the one in the notes. Complex numbers are kind of weird like that. We'll take E -1. That's the null space of A plus I. So it's the null space of 3. Whoops. Help. 3 minus 3i, 3 plus 3i, 6. And so that will be the span of, if we want, 1 minus I, -1. So I've done some simplification there. You can check that for yourself. And now what this theorem says is if I take the inner product of these two vectors, I should get 0. So let's take their inner product. So let's call this vector z, call this vector y. Then y star z is, I should take the conjugate transpose of y. So it's this. I should multiply it by z, which is this. Now 1 plus I times 1 minus I is 2. Minus 2, we get 0. Okay, so for this symmetric matrix in the notes, sorry, not symmetric, Hermitian matrix in the notes, it's true that it has real eigenvalues, and the eigenvectors coming from different eigenvalues are automatically orthogonal. When you take the inner product, you get 0. Okay, and of course, once you have an orthogonal set, you can make it an orthonormal set by dividing through by the norm. Right, so we took z was 1 minus I2, and y was 1 plus I negative 1. Did I do this right? No, 1 minus I negative 1. Yep. Now, what are the norms? Well, the norm of z is the square root of z star z. So it's the square root of, you just multiply you multiply each entry by its conjugate and add together. So 1 minus I times 1 plus I is 2 plus 2 squared, so this is root 6. The norm of y is, again, the square root of, the inner product of y with itself, which is the square root of 2 plus 1, which is root 3. And so I can get an orthonormal set of eigenvectors if I just take z divided by its norm. So it's 1 over root 6 times 1 minus I 2, and y over its norm, which is 1 over root 3, 1 minus I negative 1. Okay, again, this vector looks a little bit different from the one in the notes, but it's the same up to a scalar multiple. It's the same up to multiplication by 1 plus I over root 2, which is a norm 1 vector. So this is the same as in notes up to a scalar multiple of 1 plus I over the square root of 2. And this is a norm 1 complex number, right? That's the complex number that lives on the unit circle at the angle pi over 4. So the reason why I didn't change my computation to be equal to one of the notes is to just point out that you can get numbers that look different. You can get vectors that look different from one another, but they only differ by a scalar multiple. They can even have the same norm and look quite different. The point is, over the real numbers, there's only 2 scalars with norm 1, 1 and minus 1. So if we were computing a basis of a one-dimensional eigenspace, and I wanted an orthonormal basis, between you and me, we would only differ by a negative sign, potentially. Over the complex numbers, though, you can differ by any modulus 1 complex number. So this is the same, it's just a scalar multiple of the one in the notes. But this is actually kind of an important point, that over the complex numbers, it's a lot harder to see if one vector is a scalar multiple of another just by looking at the entries. Okay? So anyway, so now that I've divided them through by their norm, now what I have is an orthonormal basis of eigenvectors of the matrix A. Right, so if we call this one, like, I don't know, U1, and this one U2. So U1 and U2, this forms an orthonormal basis of C2 consisting of eigenvectors of A. And you can always do this, right? Because this theorem guarantees that if you have a Hermitian matrix, the eigenvectors from different eigenspaces are orthogonal. And then you can run the Gram-Schmidt process that we talked about but didn't really do anything with, to make all the bases for the eigenspaces all orthonormal bases. And then you have an orthonormal basis for all of Cn consisting of eigenvectors of A. Okay, so using this orthonormal basis, we can diagonalize A. by writing A equals Q 8, 0, 0, negative 1, Q star, where Q is U1, U2, like this. Okay, and maybe I should write the inverse here, because it turns out that Q inverse will actually be equal to Q star. That's because these are an orthonormal basis of C2. So since these are orthonormal, actually Q inverse will equal Q star. This is just the same. This is a generalization of what we learned about real orthonormal matrices, which is that their inverses were equal to their transpose. In this case, the complex setting, the inverse is equal to the conjugate transpose. But again, this generalizes the real case, because in the real case, the conjugate transpose is the same thing as the transpose. But we call matrices like this a special name. So a complex, okay, let's say a matrix Q in C n by n with the property that Q star Q equals Q, Q star equals the identity matrix. In other words, its conjugate transpose is its inverse, is called a unitary matrix. Okay, and these are the analogs of the orthonormal matrices over the real numbers whose inverses were equal to their transpose. Okay, so we of course won't have time to get to it in this course, but you can study lots and lots of properties of complex matrices. And a lot of the things that you see in the real case for real symmetric matrices translate over to the complex case, where a lot of times you just replace transpose with conjugate transpose. Of course, you still need to prove everything again because your old proofs don't work in the complex case. But a lot of the same ideas still hold. Okay, so we're going to end today, it's still several minutes to go, by looking at a bunch of results for complex matrices that should ring bells about things we learned about real matrices, just to sort of scratch the surface of the world of complex matrices. Okay, so the first thing we should state is the complex spectral theorem, which we've basically proved it, the whole thing at this point. So if A in C n by n is Hermitian, then 1, all eigenvalues of A are real. We proved that. 2, Cn has an orthonormal basis of eigenvectors of A. Okay, this is because we saw that the different eigenspaces are orthogonal to one another. And it's still true over the complex numbers that every subspace admits an orthonormal basis. We actually didn't even prove that in the real case. It's just the Gram-Schmidt process, but it still works over C. So you can get an orthonormal basis consisting of eigenvectors of a Hermitian matrix. 3, A is unitarily diagonalizable. Right, this is the analog of being orthogonally diagonalizable, i.e., there exists a diagonal matrix, and we said that all of the eigenvalues are real, so this diagonal matrix is actually an R n by n, and a unitary matrix Q such that A equals Q lambda Q star. Okay, so this is the complex spectral theorem, and again, compare it to the one from lecture 11. which said that if you have a real symmetric matrix, then you admit an orthonormal diagonalization. This is just the complex analog where essentially you just replaced the R's with C's and the transposes with conjugate transposes. Okay? 28 is where we are. Yep. Okay, and we can study positive semi-definite matrices, all these things also over C. Let me state some results. So here's a theorem. Suppose that Q is a unitary matrix. By the way, this now applies to all of the real orthonormal matrices, just like the complex spectral theorem generalizes the original spectral theorem because all real numbers are also complex numbers, and Hermitian real matrices are the same thing as symmetric real matrices. So we're going to suppose that this is unitary, but that means that it will apply to any orthonormal matrix in R n by n as well. So if lambda is an eigenvalue of Q rather, then the modulus of lambda is 1. And if U and V are eigenvalues corresponding to different eigenvectors, sorry, eigenvectors corresponding to different eigenvalues, then U and V are orthogonal. Okay, so this says that unitary matrices have nice properties. All the eigenvalues have modulus 1. In other words, all the eigenvalues live in the on the unit circle in the complex plane. And their differing eigenspaces are orthogonal to one another. Okay, note that we haven't proved this yet. The thing that we proved before was that if you're Hermitian, then your different eigenspaces are orthogonal. But here I'm not saying that Q is Hermitian, I'm saying it's unitary. In other words, its conjugate transpose is equal to its inverse. But some of the same kinds of proofs still work. So here's the proof. So suppose that X is a vector in Cn. Okay, then the length of X squared is just X star X. But now I can place a Q star Q in the middle because Q star Q is just the identity. Right? Q star is equal to the inverse of Q. And so this thing is Qx star Qx, which is the length of Qx squared. Okay, but remember that the length of X, the modulus of any vector, in fact, is a positive real number. So if the square of this positive real number equals the square of this positive real number, it means that they're the same real number. So since the modulus of any vector is a positive real number, non-negative real number, this means that actually the length of X and the length of Qx are the same. Okay. One other note is that in the notes, they sometimes use actually a fairly standard notation for the X star X. So we said that that's the inner product, and oftentimes you see this X star X notated as this kind of notation, meaning the inner product this kind of notation, the inner product of X and X. But I didn't define it last time, so, and there's no real reason to introduce it, but if you see that in other textbooks or something, in other contexts, it's just the notion of an inner product, which you will explore a little bit on the homework exercises. But the inner product that we want is the one where you multiply by the conjugate transpose. Okay, now, so if U is an eigenvector, so if QU equals lambda U, then what this equation says is that the norm of U is equal to the norm of lambda U, but the norm of lambda U is the norm of lambda, the modulus of lambda times the norm of U. And so I should assume that U is non-zero because it's an eigenvector. So this will imply that the modulus of lambda equals 1. So every eigenvector is a norm 1, a modulus 1 complex number. It's one of the ones sitting on the unit circle in C. Right, this is C. Here's the unit circle. Lambda has to be one of these complex numbers. Okay, now to show that the different eigenspaces are orthogonal, so suppose that QU equals lambda U and QV equals mu V with with lambda not equal to mu. Okay, then what we do is we just take the inner product of U and V. Okay, but now I can do the same trick again where I multiply a Q star Q in the middle here, because Q star Q is just the identity. And this is QU star QV. Okay, and QU is just lambda U because it's an eigenvalue, and QV is just mu V. And so this thing becomes the conjugate transpose of lambda U, which you take the conjugate of lambda and the conjugate transpose of the vector U, right? Because you have to conjugate the whole thing. So any scalar gets conjugated. This is times mu V. And so you get lambda bar mu times U star V. U star V. Okay, now this means that lambda bar mu equals 1, right? Because this thing and this thing are equal. But remember now that for a complex number with modulus 1, the conjugate is equal to its inverse. So recall that if lambda bar equals 1, the modulus of lambda is 1, then this means that the inverse is equal to the conjugate. You can just check this. That's because you have to add the angles, so you just take the opposite angle okay, across the real axis. So this means that lambda equals mu, but we assume that lambda wasn't equal to mu, which means that, assuming that U star V is non-zero. So maybe I should say this. If U star V is non-zero, this implies this, which implies this. So all this means that U star V has to equal 0. Which is what we wanted. Okay, let me point out a really technical thing that the notes get a little bit wrong. They call this thing the inner product of QU and QV, but it's actually not. This thing is the inner product of QV and QU. And I wonder if I actually got it wrong in the notes last time. Let me just see. Yes, I kind of did, because I didn't really, because I didn't define that notation. But this is the Hermitian inner product of W and Z. So you might use the notation the inner product of W and Z is Z star W. Okay, this is actually important because for something to be an inner product, it needs to have the correct properties in both of the arguments. And if you do it the other way around, it doesn't have the correct properties. Okay, so I never actually said what order you would say that this is the inner product of, but I'm now telling you that the inner product of W and Z is Z star W. The inner product of Z and W is W star Z. Right, but we already said that these things aren't always the same. Okay, so this is a technical point, but I think technically the notes are wrong on this. But the result is still true. That if you have a Hermitian matrix, then if you have a unitary matrix, even if it's not Hermitian, which it won't be in general, if you have a unitary matrix, all of the eigenvalues have modulus 1, and the different eigenspaces are orthogonal to one another. Okay, and then you can do all the stuff with positive semi-definite matrices in a more general context over C. So let me just say this. So note that any matrix of the form B star B is Hermitian, since of course if you take the conjugate transpose of this thing, you take the product in the opposite order, but you take the conjugate transpose twice, you just get the matrix back. This is kind of like for the real case saying that A transpose A is always symmetric. But remember, things that look like A transpose A had a special name in the real case. Those were called positive semi-definite. The generalization to the complex case is things that are of the form B star B are called positive semi-definite. And remember last time it was only defined for symmetric matrices? Well, a Hermitian matrix A, and C by n, that means it's equal to its conjugate transpose, is called positive semi-definite if A equals B star B for some matrix B in C K by n, right? So all the theory of, or a lot of the theory of positive semi-definite matrices that we developed for real symmetric matrices have the analogs in the complex case. These Hermitian matrices play the role of the symmetric matrices, essentially. Okay, so it's still true, for example, that if you have a positive semi-definite matrix, all of the eigenvalues of real are non-negative real numbers. So that's a thing that we learned in the real case. It's still true in the complex case, taking this definition of positive semi-definite, which is the more general definition. So I guess that's the last thing we'll cover today. So if A is positive semi-definite, then all of its eigenvalues are non-negative real numbers. Okay, now looking at the time, I actually don't think I have enough time to prove this, but the proof is in the notes. The point is just, we spent a decent amount of time learning about positive semi-definite, positive definite, symmetric matrices in the real case. We had homework problems, we spent several lectures on it, and a lot of those theorems generalize kind of naturally to the complex case, and there are good reasons to generalize to the complex case. But just like you learned linear algebra the first time over the real numbers, learning that theory for positive semi-definite matrices over the real numbers first, like, essentially gives you all of the ideas of what kinds of things are true and why. And then when you learn it a second time over the complex numbers, because you're learning it a second time, things become sort of clearer or more intuitive for you. Okay, so in some future classes, you may learn about these things over the complex numbers, but you'll have the intuition from this class to guide you. Okay, so next lecture we'll talk about Fourier analysis. I guess that'll be the last lecture of the course. So see you then.